Hello and welcome to part one of our tutorial series on plasma diagnostics. I'm Jia Han from UCLA's Basic Plasma Science Facility. This is a two-part series introducing the fundamentals of plasma diagnostics, with an emphasis on practical insights and experimental subtleties that go beyond textbook discussions. In this first video, I will focus on intrusive diagnostic methods such as probe-based techniques. Part 2, which will be released later this month, will cover non-intrusive diagnostics, including laser and spectroscopic methods. If you find this video helpful, please consider subscribing to our channel and stay tuned for future tutorials. Let me start by introducing the term plasma diagnostic. Why don't we say we measure the plasma, but instead that we diagnose it? I will answer this question by a simple analogy. Imagine you're a doctor and your patient is a baby who can't talk. You want to understand what's going on inside, the baby's temperature, heartbeat, or condition. But the baby can't tell you directly. That's our plasma. You can poke it gently with a stick. That's a probe, an intrusive diagnostic. You'll get local, detailed information, but the baby might start crying or worse. That's plasma perturbation. Alternatively, you can use ultrasound to look inside without touching. That's like non-intrusive diagnostics such as laser scattering or microwave interferometry. But even with ultrasound, you don't see everything. You get a limited view, sometimes just an averaged snapshot. So plasma is never measured directly. We diagnose it. Just like in medicine, each tool gives us partial information, and we interpret the results to understand the whole system. Every diagnostic has its trade-off. And just like in medicine, diagnostics can have side effects on the subject itself. Here's a quick overview of what we'll cover in this video. I'll focus on the key ideas rather than every detail, but you'll find extra reading materials in the video description if you'd like to learn more. All intrusive diagnostics share one thing in common. They interact directly with the plasma. That usually means probes. Electrostatic probes collect particles, magnetic probes sense magnetic field changes, and resonator probes detect how waves respond to the plasma. These are the three major probe categories, but there are more beyond them. If you would like to know more about a specific probe, feel free to leave a comment. I'll do my best to respond or point you to additional resources. I'd like to share with you next on what I call the life cycle of a probe. Before building any probe, you need to have a brief idea on the plasma environment you'll be working in. The first step is to define your goal. What parameters to measure? Is it density or temperature or both? And at what spatial and temporal resolution? Once you know that, you can estimate the expected signal, its amplitude and frequency, so you can decide on electronics and data acquisition system needed to capture the signal accurately. Next, choose a probe geometry and materials that are suitable for the plasma environment while keeping perturbation under control. Then, build and calibrate the probe, first on the bench, and if possible, in a known plasma before using it in your main experiment. Now you are ready to acquire data. Start with a simple model to interpret your data in real time, once you've collected a data set. Analyze it carefully, compare with your model, and refine both your design and interpretation. This process is iterative. Almost every diagnostic takes several cycles of improvement before it works well. I'll show this same roadmap again in part 2 when we talk about non-intrusive methods, and you'll see that the overall process is remarkably similar. The first category I'll talk about is electrostatic probes. These are probes that directly sense particle flux. While there are many kinds, Langmuir probe is the foundation of all of the following under this category. Imagine it's 1920. You are Irving Langmuir. You have just made a glowing gas inside a glass tube, but no one really knows what it is. You decide to do the simplest possible experiment. Poke it with a wire and see what happens. You grab a piece of metal wire, stick it into the plasma, connect it to a voltmeter, and measure the potential relative to ground. You read a number from the voltmeter. What does this number mean? To help answering the question, I will explain briefly what happens when plasma meets a surface, or the definition of plasma sheath. Imagine a plasma that is quasi-neutral, which means there are equal number of electrons and ions. This is usually a good assumption. When this plasma touches a metal surface, electrons, being lighter and faster, arrive at a higher rate than the positive ions. It's like playing Mario Kart with a motorcycle. You're lighter and faster, so you reaches the head of the group first. If the metal is isolated, the electrons accumulate on the surface and the metal becomes negatively charged. This leaves a thin layer of positive charge behind, creating what we call the plasma sheath. An electric field forms across this sheath, slowing down the electrons and attracting positive ions towards the surface. This field adjusts until it reaches equilibrium, where total current to the surface is zero. So how does all this relate to measuring plasma voltage? Let's find out. Now, going back to the previous question, what is it that you're measuring when you put a voltmeter across a plasma? The answer is you're measuring the potential of the surface such that the total current to the surface is zero. People have a name for this number. That's called the floating potential. With the understanding of the floating potential, we can expand this to understand electrostatic probes. Essentially, it is biasing that metal wire you put in the plasma positively or negatively with respect to the bulk of the plasma, defined as ground, and measuring the current that is drawn. On the left of the appeared IV curve, the probe is biased negatively. Electrons are repelled and only ions reach it. That's the ion saturation region. As we increase the bias voltage positively, we will reach the floating potential where the total current is zero. Keep increasing, we get to the transition region where electrons start to overcome the potential barrier and reach the surface. For Maxwellian distribution plasma, this region follows an exponential curve, and its rising rate gives the electron temperature. When probe reaches the plasma potential, all locally available electrons are collected because of their thermal motion, and increasingly positive biasing cannot collect any more current. In reality, this current tends to increase more due to factors like sheath expansion. This is the basic of how Langmuir probe works. When I started introducing electrostatic probes, I had described them as probes that directly senses particle flux. These probes directly collect particle fluxes, but are never a direct measurement. Every surface in the plasma has a sheath around it, and this is always a perturbation to the local plasma environment. Plasma parameters such as density and temperature can be derived from the measured signal using some kind of assumptions and theory. The challenge of electrostatic probes, or perhaps any probes, isn't about taking the measurement, but how to interpret the data. In this case, it is the understanding of how probe changes the plasma around it, and what that means for the unperturbed plasma. Now, if we dive into the theory of sheath and probes, this tutorial will become substantially long and dense. Instead, I will list a few aspects of consideration about electrostatic probes. The first thing I will talk about is probe geometry, and I will start by talking about probe size. We know that probe perturbs the plasma locally, which means if the probe size is too big, it will cause too much of a local perturbation. On the other hand, since probe collects current, its size is directly proportional to the measured signal level. So if the probe is too small, we will not measure a strong enough signal above noise level. Note that these 2 points are applicable not only for electrostatic probes, but also magnetic and resonator probes I will talk about later. The next thing I want to talk about when discussing probe size is the effective collection area. That is, the apparent area of the probe as seen by the plasma. We know that any surface in a plasma collects particles through its sheath, that thin region where electric fields accelerate or repel charged particles. You can think of the sheath as an invisible net surrounding the probe. The probe repels a species, for example, a negative probe repelling electrons, the net tightens, and the effective area shrinks to just around the probe tip. When the probe retracts a species, and positive probe attracting electrons, the net bulges outward. So particles are collected from a larger region. Without diving into detailed sheath theory, I will also note that sheath thickness scales with the Debye length, which itself is inversely proportional to the square root of the plasma density. So, the same probe geometry can collect very different currents depending on the probe bias and the local plasma conditions. That means, if I try to calculate density using just the physical size of the probe, I'll be wrong, because the effective collection area changes with plasma parameters. In fact, even within the same discharge, it can vary significantly. The sheath near the dense plasma core is thinner than that at the low-density edge. Now, let's talk about the shape of the probe. The simplest geometry is a planar probe. Under the simplest assumption, it can be treated as a one-dimensional system. The surface area is much larger than the sheath thickness, so everything happens more or less perpendicular to the surface. The orientation of a planar probe plays a major role. The probe only collects particles on its surface. This property was cleverly used to invent the Mach probe, which uses two or more planar surfaces facing different directions. By comparing the ion fluxes collected by each face, we can estimate the direction and relative magnitude of plasma flow. However, this only works if the sheath is a thin layer tightly attached to the surface. Once the sheath expands significantly, edge effects appear, and no simple analytical solution exists. This is also why Mach probes can fail. Their readings depend strongly on the sheath's shape and size, not just on the plasma flow. Next, let's look at cylindrical probes. Earlier, we used a metal wire as an example. That's essentially a cylindrical probe. Good news is that there are analytic models for this geometry. Bad news is these solutions can be complicated. Here I listed some of the most common theoretical models. Special note on OML, the simplest, but very restricted in applicability because of its assumptions. If you want a quick estimation of your plasma parameter based on ion current, this is usually the go-to theory. Finally, there are spherical probes. They are orientation independent, collecting current uniformly from all directions. This makes them ideal for space applications, where a satellite or spacecraft may rotate freely relative to the plasma flow. This simplifies the interpretation of current voltage data. Most of the sheath theories developed for cylindrical probes are also solved for spherical probes. What critical factors should you watch for in the plasma environment of interest that can significantly influence the measured result? Here are some key conditions. The first factor is high neutral pressure. As pressure increases, charged particles collide more frequently with neutrals. Among all collision types, electron-neutral collisions usually have the shortest mean free path. If that number becomes comparable to the sheath size, it means collisions are starting to affect how particles reach the probe, and that's when you really need to pay attention. Next is the magnetic field. It changes the sheath structure and makes probe readings depend on how the probe is oriented. In magnetized plasmas, you might need to use modified models to interpret the data accurately. Basic probe theory assumes a Maxwellian plasma, but energetic particles break that assumption. Similar to magnetized plasma case, modified models are needed for data interpretation. RF plasmas are common in processing, but RF fields can easily distort probe signals. To counter this, researchers have developed different RF compensation schemes. Most of them requires a special compensation circuit placed as close to the probe tip as possible. Special theories also exists for analyzing RF distorted probe signal. Finally, in chemically active or dusty plasmas, the probe surface contamination or secondary electron emission can significantly alter signal collections over time. Choosing the right material and implementing a regular cleaning or conditioning procedure are key to maintaining consistent measurements in this case. I won't go over each of these factors in detail as they are already well covered in existing literatures. Instead, I would like to introduce one example of classic probe perturbation. During my thesis work in 2020, I faced a challenge when attempting to measure how my plasma was evolving over time using a Langmuir probe. The plasma evolution was faster than my RF compensated probe sweeping circuit could measure. To get around this, I used the step sweeping technique, which is applying a fixed bias voltage for a short period, then stepped through different voltages to reconstruct the IV curve at each moment in a series of identical plasma pulses. When the probe was biased to collect electrons, I noticed something unexpected. If the bias was on for too long, the collected current gradually dropped over time, even though the plasma settings didn't change. After running multiple tests, we found that this effect was independent of probe shape, size, material, or electronics, but became stronger at higher densities. It seems that locally plasma is depleted by the applied bias voltage, a classic case of probe perturbation. In this experiment, we were using a small volume plasma chamber with insulating chamber wall, which is typically the case in plasma processing. Possibly what happened is in a confined plasma, the probe drains electrons faster than they can be replaced locally. As a result, the local plasma potential changes, and plasma is depleted. A similar effect can also happen in magnetized plasmas, where the probe draws electrons along a finite field line, effectively depleting the plasma along that flux tube. This reveals an important point. The probe biasing time must be managed carefully. The timescale must be long enough for the sheath to form, but can't be too long such that it depletes the plasma. There is no single safe biasing time. It really depends on the specific plasma conditions in each experiment. However, a simple test can help. At the start of any Langmuir probe experiment, vary the probe settings and check whether the measured current stays consistent. If it does not, you have gone beyond the time window where the measurement remains reliable.
Here's a summary of the key factors to consider when using electrostatic probes. All of these effects should be evaluated before probe construction, even if it's something as simple as a piece of wire. Even with all the factors considered, you still need calibration. This is extremely important because of the probe's collection area issue we mentioned earlier. As I mentioned earlier, all electrostatic probes are essentially variations of the Langmuir probe. I've already discussed the Mach probe briefly, and next I'll move on to emissive probe and energy analyzer, which are a bit more complicated and introduce some additional concepts.
An energy analyzer, by its name, measures the energy distribution of selected charged particle species. The simplest version is a retarding field analyzer. It consists of an entrance grid that lets plasma particles in, one or more biased grids that create an adjustable electrostatic barrier, and a collector at the back. As we vary the grid voltage, only particles with certain energy make it through to the collector. By recording IV curve, we can determine the cumulative energy distribution, and by differentiating that curve, we obtain the energy distribution function. Energy analyzers are widely used in plasma processing, where understanding the ion energies impacting surfaces is critical for processes such as etching. They can also be adapted to measure electron energy distributions. However, it is almost impossible to get an accurate measurement of the local bulk electron properties because the sheath around the probe modifies the energy and number of electrons entering the analyzer. In both cases, it is important to prevent secondary electron emission when particles hit the grids. Otherwise, the analyzer's readings won't be accurate. An emissive probe is a Langmuir probe using a heated filament as its probe tip and is heated to emit electrons into the plasma. At the point where the emitted and collected electron currents balance, the probe potential equals the plasma potential. This is a powerful diagnostic in situations where accurate plasma potential, especially potential fluctuation, measurements are needed, for example in sheath studies or electric field mapping. A Bdot probe, or magnetic pickup coil, is the workhorse of time-resolved magnetic diagnostics. The principle is based on Faraday's law of induction. A changing magnetic field induces an electric current in a circuit. The probe directly measures the time derivative of the magnetic field. By integrating this signal, we recover the actual B. In experiments, Bdot probes are placed inside the plasma to measure field fluctuations, wave propagation, mode structures, or instabilities. Plasma current can also be inferred from Bdot result. A single-loop Bdot probe doesn't only respond to change in magnetic fields. Like described previously, plasma is conductive, so any wire placed inside can act like electrostatic probes. Electrostatic coupling between the probe wiring and plasma, undesirable RF or capacitive noise from the discharge, ground loops or induced voltages along the cable can all affect measured signal quality. One solution to these problems is differential Bdot probe. This is constructed using two identical coils wound in opposite directions, clockwise and counterclockwise. The signals on the two coils are subtracted, so their magnetic contributions add up, while the electrostatic pickup corresponding to the noise cancels out. In the case of more than two coils, it will be two groups of coils consisting the same number of turns. Another solution is to coat the coils with insulating material, or frequently putting a glass or ceramic sleeve over it. This is also important so they do not draw current from local plasma. The diameter of the protective sleeve will set the minimum spatial resolution. The picture on the left here shows a probe measuring three orthogonal components of the magnetic field. This is pretty common to get a full view of waves or instabilities in the plasma. Experience has shown that the orthogonality between the loops are key for accuracy of the measured result. As we are talking about physically inserted probes, naturally the question of probe perturbation arises. One opinion is the probe body and its sheath can perturb the local current and field distribution. In order to see how much this is a problem, I have conducted an experimental test in the past where I made 4 Bdot probes of different size and measured magnetic field under the same plasma condition. If you're interested in the detail, you can find more information in my thesis. But the short conclusion is only at very high neutral pressure, so high collisionality, the bulkiest probe measures different result compared to the others. Ian Hutchinson has a good explanation in his book about this result. The magnetic fields are generated by currents throughout the plasma, not just locally near the probe. In other words, the field at the probe is obtained by an integral of the Biot-Savart law over all the relevant space. Therefore, even though the perturbation to the local current density due to the probe is large, an insulating jacket prevents all current from flowing through it. The local magnetic field may be scarcely perturbed at all. So probe is geometrically too large if the sensor size is comparable to the gradient scale length, that is, if you're trying to measure a structure that is physically the same size as your probe, or if the sensor substantially changes the macroscopic characteristics of the plasma. This can be typically verified by placing another probe next to it and see if the signal on the other probe changes as you insert this probe. To summarize, a well-designed Bdot probe uses very small coils, thin dielectric coatings, and sometimes differential pairs to cancel noise. Some of the elements to consider before you start building your own Bdot probe includes frequency response and plasma properties. This determines the number of turns and loop size of your probe, as well as what electronics to use for getting the signal. Plasma property also govern the decision for what materials to use. It must survive the high temperature plasma environment. Again, calibration is crucial. The coil's area and number of turns must be known. If the probe is used to measure more than one component of the magnetic field to measure structure, the most important construction tip is to make the loops such that they only pick up field from one direction. A tuning fork has a natural pitch, a frequency that depends on its stiffness and the medium around it. If you strike it in air, it rings at one tone. Dip it in water, that tone changes because the surrounding medium affects how it vibrates. The same idea applies to resonator probes in plasma, which is a miniature microwave cavity or quarter wave transmission line that rings at a particular frequency when you immerse it in plasma. Or the dielectric constant changes and its resonant frequency shifts. From the shift in resonant frequency, one can derive the plasma frequency, which in turn gives the plasma density. A resonator probe was invented by Rainer Stenzel in the 70s. People also call it hairpin probe because the shape of the resonator looks like a hairpin, although this is not necessarily the only shape that would work. In a typical hairpin resonator probe, two small coupling loops are used. One loop is placed close to the hairpin to excite it with a microwave signal, while the second loop is positioned nearby to detect its resonant response. To operate the probe, you need microwave electronics to scan through frequencies and identify the resonance peak. The hairpin structure itself needs to be exposed to the plasma, but the supporting structure is frequently covered in dielectric to protect it from the plasma. These protective dielectric coatings can make the probe physically bulky. An alternative construction uses a single coupling loop for both transmitting and receiving the signal. This simplifies the design and reduces the probe size, but it typically produces a weaker signal. The choice of natural resonance frequency of the probe F0 is closely related to the density range of interest. Propagation of an electromagnetic wave traveling through a plasma is cut off at a critical density. A larger F0 is needed in denser plasma. However, if F0 is much bigger than the plasma frequency, the measured frequency shift will be negligible. and thus sensitivity of the probe is limited by the microwave electronics. In practice, the simple equation doesn't always work. The simple theory can be modified by, for example, the presence of magnetic field. In this case, probe orientation might cause splitting in the resonance peak. The extra dielectric coating applied to the structure also confines part of the field in the dielectric, making the probe less sensitive and shifting its baseline frequency. In addition, even though hairpin probes do not draw current from the plasma or pick up potential oscillations, it is still affected by the sheath around the wire. If the wire spacing is on the same scale as the dBi length, the sheath effect cannot be neglected. That wraps up today's tutorial. I hope you found it useful. For those interested in exploring this topic further, I encourage you to check the video description for related literature. Feel free to leave any questions or feedback in the comments. Please consider subscribing so you don't miss future uploads. Thanks again for watching. I look forward to seeing you in our next video about non-intrusive diagnostics.